In this video we're going to be talking about how we solve a simple circuit problem which we did back in lecture 6. So I am going to call this a t-junction problem because I don't really know the other way to call it, and the reason I'm going to call it a t-junction problem is because it looks a little bit like a letter T. So this is the type of problem that you'll be facing. So in this sort of problem we're asked for the circuit shown determine the voltage drop across each component and the potentials at points VA, VB and VC. And this is one I set you a while ago and I gave you the answer of 54 volts. So what we've got here is we've got the current flowing through two resistors, and then we've got an unknown current at the bottom, I3. So first up, let's define some voltages. So we know the current is in the downwards direction, so that means I can define the voltage as being in the upwards direction. So I'm going to call this V1, you can call it V5K, you can call it whatever you want, and it's going to be in that direction. Then the current continues downwards along this branch, and then we can say that the voltage drop across this 4K resistor is going to be in the upwards direction, and I'm going to call that V2. You can call it V4K, you can call it whatever you want, but the voltage is opposing the flow of current. Then finally I'm going to define a voltage across this final resistor. I'm going to call that V3 because that's the voltage drop across my third resistor, and it's also in the opposing the flow of the current, which has been defined as I3. So what I'm going to do now is I'm going to find out what's going on. So I can calculate V1. Remember Ohm's law, so we've got V is equal to IR, always, always, always. So V1 is going to be equal to the current flowing through that resistor, which is actually given in the question as being 6 milliamps, multiplied by the value of the resistor, which we can see is 5 kilo ohms, and this will give us V1 is equal to 30 volts. Next up we can calculate V2, so once more this is going to be the current flowing through that resistor, which as we can see this 6 milliamp current is going to keep going down and down and down and down. So we know that's also 6 milliamps because there's nowhere else for it to go in this case, multiplied by the value of this resistor, which is 4 kilo ohms, which will give us a voltage drop of 24 volts. Finally, let's do V3. To do this, we need to find the current flowing through it, which is I3, which is given in the question here, multiplied by the value of the resistor, which we know is 2 kilo ohms. However, to solve this, we need to find what I3 is. And this is when it comes to, this is why I've called it a t-junction problem. So we've got the current flowing in to one point, and this is 6 milliamps. And then we're also given, at this junction point, the current flowing out is equal to 1 milliamp, which we've got in the diagram above, and we've got another wire coming out of here. And this is essentially a version of Kirchhoff's law, which we've used intuitively before. So we know that current in is equal to current out, so we can see we've got 6 milliamps flowing in, 1 milliamp flowing out. Therefore, what must be going on here is we must have a current of 5 milliamps flowing out down that final branch. So therefore we can see that I3 is 5 milliamps. So we can just substitute that into our equation. So we've got 5 milliamps times 2 kilo ohms, which will give us an answer of 10 volts. So that's the first part done. We found the voltage drop across each component. Now what we're going to do is we're going to find the potentials at points VA, VB and VC. I'm going to give myself a bit more space. So we know that the voltage drop here is equal to 30 volts. We've just calculated that. We know the voltage drop here is equal to 24 volts because we've just calculated that again. And we know the voltage drop here is 10 volts because again we've just calculated it. So when we're finding the potentials at points VA, VB and VC, what we're essentially doing is we're starting at 0 volts. This is our starting point. And the potential at point VB, we can see that that just contains that one resistor. So the voltage difference between here and here is just that 24 volts that we've got before. So we can say that, I'll write it over here, VB is equal to 24 volts. What's the potential at VA? Well, I'm going to draw a line across my potential here, and imagine your oscilloscope probe, okay? You've got your black cable connected here and your red cable connected here, and you're measuring that voltage. So this is the potential, VA. And I'm sorry about the wiggly line, I don't have the best straight line drawing. So what we can say here is that this potential, we've got the 24 volt potential here and a 30 volt potential here, so we can say that VA is equal to, well, the 24 plus 30, which is equal to 54 volts. And now we're going to do VC. So potential VC, this is the point here. And remember, you've still got the black lead of your multimeter connected to the 0 volt point, and this time you've got the red cable connected to this point. So we're effectively looking at what happens in this direction. And this time, because that potential drop across that resistor is going against the direction that we're defining, we can say that VC is equal to minus 10 volts from the reference point. And that's how we find each of those answers. So that's the procedure. Start with what you know, starts with Ohm's law, and then see what you can find out.